All right, here we are with Module 10, Lecture Notes 19. Today we're going to be talking about acids and bases. And I'm guessing in maybe some of your physical science courses in your earlier years, you have done some things with these two words, acids and bases. And they're a lot of fun to experiment with because a lot of these things can be found in our homes or in the kitchen. So today we're going to go a little bit deeper and look at some common properties of them. So the first thing we're going to note is that for acids and bases, it talks about their taste. Acids, if you were to taste them, taste sour, and bases taste bitter. Sour would be like citrus fruits. Lemons, limes, oranges, that pucker comes from the acidity of citric acid. And then bases would have a bitter taste. If you've ever accidentally gotten soap in your mouth or shampoo, soaps and cleaners tend to be bases, and that's where that bitter taste comes from. Now, real quickly, I just want to note that if you're doing an experiment in a chemistry lab, you should never ever taste anything unless your teacher tells you to. You should never use taste as a way to experiment with acids and bases unless you're instructed to do so, because it could be really dangerous. The second property it talks about is with acids that they're going to conduct electricity in water. And we're going to leave that for a second. We'll visit it later on down here in the page. And then lastly, it talks about what happens when you do a litmus test. And this is what you're going to be doing in lab. You're going to have little strips of litmus paper, and you're going to be testing acids and bases. Depending on what color the litmus paper turns, you will know whether you have an acid or a base. Okay? Litmus paper comes in two colors, red and blue. And so if you take a blue piece of litmus paper and it turns red, you know you have an acid. I always remember that red is trying to signal that an acid is present. And then the opposite would be true for bases. If you have a red piece of litmus paper and it turns blue, I remember bases, blue for bases. They both start with B. Okay? And then also for bases, note that they tend to be slippery to the touch, and that falls true with our soaps and cleaners as well. So these properties are just things that you should know about acids and bases. All right, so what technically is an acid? Your book defines an acid as a molecule that donates a proton or an H+ ion to a reaction. It is a proton donor. And then base would be the opposite. It would be the compound that accepts or receives that proton. It is the proton acceptor. Okay, and you can see here H+, it's just the hydrogen ion. It is just a single proton. Okay, let's jump into these two examples. We're going to try to determine which of these compounds is acting as the acid and which one is acting as the base, and we're going to label them. All right, in the first one, you can see we have HCl mixed with some water, and in the end, we end up with H3O+ and just chlorine by itself. I often look at the products, and that gives me a big hint to figure out who donated the proton and who accepted it. Okay, I notice here that water looks a little different. It now has an extra proton. So what must have happened is that the HCl donated a proton to water. Now chlorine ion is by itself, and that's how this reaction went forth. So looking at these definitions, the donor is always the acid, and the acceptor is the base. Okay, let's go to the next example. I want you to try to label the acid and the base out of these two molecules. Again, you can probably look at the products for a little bit of help. You had NH3, and after the reaction's finished, you have NH4. So you know that NH3 received something extra. So in this case, the donor acid and the acceptor is the base. What I want you to see from these two examples is that water, in the first example, acted as a base, and in the second example, acted as an acid. Water is amphoteric. Okay, remember the prefix amph, kind of like an amphibian. It likes to be on land and water. Well, amphoteric, amph, means it can act as either an acid or a base, and water is a great example of that. Okay, the next thing your book talks about in this section is what happens to ionic compounds when they dissolve in water. So if we were to take an ionic compound like sodium chloride or salt, and we were to dissolve it in some water, what would happen is it's going to split apart into ions. We would end up with sodium floating around and chlorine floating around. Okay, and I drew those as ions when they are not in their ionic bond. So when ionic compounds dissolve, they actually break apart. Okay, and this is why if you take an ionic compound and you dissolve it in water, like take salt and dissolve it in water, and you stick a piece of metal in it connected to a battery and a light bulb, you can actually light up the light bulb simply from the charges that are floating around in that solution. You can conduct electricity from an ionic compound because it breaks apart and has all these positive and negative charges floating around in the solution, which is pretty cool, I think. Okay, let's flip over to the back and look at some common acids and bases. So the way that you usually know that you are looking at an acid is you're going to see hydrogen as the first atom in the chemical formula. I have a list of acids here, and notice that all but one of them have hydrogen as the first atom. Listen to these common acids: hydrochloric acid, hydrobromic, hydrofluoric, nitric acid, sulfuric acid, phosphoric acid, carbonic acid, and acetic acid. Lots of these had your polyatomics that you memorized in them as well. Luckily, you do not have to memorize these acids. They are in a small box at the top of your periodic table. So if you get a problem and you need the formula for an acid, they're really easy to remember because it's just hydrogen with that polyatomic, but you could always check yourself with the list that's right here. Most bases have the hydroxide ion in them. Okay, hydroxide is OH, and when you're crossing it and making a formula, hydroxide always has a 1- charge. All right, in this section, we're going to look at what happens if you take an acid and react it with a base. It will always produce a salt and water. The word salt here, used in this sense, is just talking about an ionic compound. It's used as a generic A, salt, and water. And water, we know, is always H2O. So if you take an acid and a base, they're going to react and rearrange and form two new things. So let's jump right into a problem and work through it completely together. They want us to react hydrofluoric acid reacts with potassium hydroxide. We have an acid and a hydroxide, which is a base. hydrofluoric acid, we know, is hydrogen with fluorine. You can check your formula here. And it's going to react with potassium hydroxide. Now, before you just throw potassium and hydroxide together, please be careful to check the charges. Potassium is in the first column. It likes to be a +1, hydroxide a -1. So when you cross and reduce, you end up with KOH. All right, so acid and base makes a salt and water. Now, how do we get these? The trick that I've always used, and it really works, is to say to myself, outsides, insides. So what that means is you're going to take the ions on the outside and they're going to become partners, and the insides will become partners in our new arrangement. So if hydrogen and hydroxide are new partners, HOH, that's where I get the water, H2O. And now I need to pair up the insides, fluorine and potassium. So am I going to make fluorine potassiumide or potassium fluoride? When you write the ionic compound, please be careful to always write the metal first. And you can probably hear, if you say it to yourself, it sounds better, potassium fluoride. You also need to check charges. Okay, so I'm going to be crossing potassium with fluorine. They are both 1 charges, so KF will be your formula for potassium fluoride. All right, last step is to balance. Remember the balancing stuff. We need to make sure we have the same number of each element on both sides. All right, 2 hydrogens. Check. 1 fluorine, 1 potassium. Oh, that's dry. Let's try red. 1, 1, 1, 1. Okay. I would like you to start on the next problem, see how far you get, and we will check it together. Hydrochloric acid reacts with rubidium hydroxide. I'm going to create new partners. The outsides, HOH, give me water. And on the inside, I have chlorine pairing with rubidium. And if I cross rubidium 1+ with chlorine 1-, I get RbCl, rubidium chloride. This one is also balanced the way it is. Both of these first examples used monoprotic acids, which just means that it's an acid that only donates 1 hydrogen. Okay. In this next example, we're going to look at an acid, sulfuric acid, that has 2 hydrogens, H2SO4. Okay, it works the same way, but when you balance your reaction, you may need to use more than just ones. All right, in this one, it wants sulfuric acid to react with sodium hydroxide. Sodium is a 1+, hydroxide is a 1-, so we are reacting NaOH. All right, we're going to do our outsides, insides. The outside is still going to make water. We have some extra hydrogens pairing with hydroxides. We're still making the compound water, but we will have to figure out how many waters when we go through and do our balancing later. And then on the inside, we're pairing up sodium with this polyatomic sulfate. Do you remember sulfate's charge? If you don't, you might have to look it up, but we are crossing sodium, which is in the first column, with the sulfate ion, SO4 2 minus. So we're going to cross, and you end up with Na2 SO4. Okay, now we can see we need some balancing here. I see that there's 2 sodiums on the right, so I'm probably going to need to make 2 on the left. And then let's add up how many hydrogens we have. We have 2 here, and we have 2 more. So if I have 4 hydrogens on the reactant side, I probably need 2 times 2 to make 4 hydrogens on the product side. Okay, so I think 1, 2, 1, 2 will balance this. All right, the true test of whether you really have this. Try to press pause and do the whole thing by yourself. I know it's tempting to just play through and watch me work it out, but please practice working this out while it's fresh in your mind. All right, I have hydrobromic acid reacting with barium hydroxide. When I cross the charges, barium is a 2, so that's where I get this subscript here. This part has to be right in order for your balancing to work out in the end. If you do outsides, hydrogens and hydroxides make water. And then on the inside, barium needs to pair up with bromine. Again, barium is a +2, bromine is a -1. So that's why I have them crisscrossed that way. To balance, I think we need a 2 here and a 2 there. And in all of these reactions, notice they follow the same pattern. An acid and a base make a salt and water. Thanks for listening, guys.